Welcome back to the fourth video of the series. There is plenty of work waiting for us today. First, we're going to raise a regular maskable interrupt and simulate the PIC or programmable interrupt controller to see how the CPU is given the vector number of the handler to be executed as a response. Then we're going to replace the old manual clock and reset signals with the proper square wave generator and add a text LCD to our computer. That's a lot to squeeze into one video, so let's get started. As a quick reminder from the previous video, when an interrupt is raised, and now I mean the regular maskable interrupt raised by the inter pin, the AT86 acknowledges it by setting its int A output to 0. This is a signal to the PIC that it needs to provide the CPU with the vector number to be called. It means that we need to have something which can drive the data bus bits when and only when the int A is active. Do you remember when we tried to simulate the program memory with 8 resistors which set zeros and ones on the data bus to form the NOP machine code? Today we will do a similar thing, but more digitally if you want. We're going to use the 74HCT244, which is a tri-state 8-bit buffer which drives its outputs only when an additional signal is given. This signal is very similar to the CE or chip enable in the memory chips. If you need more explanation of what a tri-state output is, look around my channel, as this is explained in my separate series where I talk more about the 7400 chips family. This is what we need to add to our breadboards. The outputs of this chip are activated by a low signal on the 1G and 2G inputs. There are 2 inputs because each of them drives 4 outputs separately. We will simply short them together and connect to the int A output of the CPU. So this chip will talk to the data bus only when the CPU acknowledges the interrupt. We will set the inputs to a number which is easily recognizable in binary, let's say 01010101 or 55 hex. But first let's start with modifying the interrupt inputs signals. Currently the NMI had this wire and the resistor pulling it down, and the inter was just put to the ground. Now we need to switch that. We are not going to use NMI. Yeah, inter input is pin number 18, just next to the clock signal. Okay, so now we are done. We can then raise an interrupt by switching this wire to VCC and then go back to the ground. Now let's build in the 74244. I think this is a good space for it. And now I need to get all 8 bits of data bus from here, because unfortunately there is no space around the CPU nor the memories. Let's get started. Now I currently connected all the data bus to the outputs of the 8 buffers in this 74244. Now I need to connect the gates, the enable signals from pin 19 and pin 1 together, and to the int A signal, which will trigger this buffers to send the signals on the data bus. As ever, I need to remember about power supply for the new chip. So now let's set all the inputs of the 8 buffers to this pattern we chose, which was 010101. I think we are done here. The last thing I'm going to do is to add this LED to our int A signal, which is active low, so I need to put the anode of the LED to VCC, and the cathode goes to the int A. It should light up when the int A is active. Before we see it working, first let's have a look at today's program. It is almost identical to the previous one. There are three differences. One is the vector we set up. Now the DI register is initialized with 55 hex times 4, as we want to use the vector number 55 hex. The second difference is the change to the handler label name. I updated it to int_handler, which makes no difference for the compiled program. It is purely a cosmetic change. Finally, the last difference is the additional instruction STI. After reset, the CPU is configured to ignore interrupt requests. STI enables them. As previously, I already have stepped through the initialization part of the program, and the CPU is about to enter the infinite loop. So what we can see is our address set to F0016. So it addresses the NOP instruction in our infinite loop. Let's go 1 or 2 steps through that. As we can see, NOP 90 is our first instruction. Okay, now let's raise the interrupt. So I'm switching this wire to VCC, and it needs to be held high until the int A signal gets active. It's not yet there. And there you go. Look at that. Int A is now active. So, and also what's happening? We've got 01010101, which is our 55. That's the byte set by our 8 buffers, which now became active on the data bus. So this tells the CPU which vector to use to handle this interrupt. I didn't tell you this before, but in fact, the CPU raises the int A signal twice. First time, it tells the PIC just to freeze its listening to its inputs. If any other interrupt line becomes active, just ignore it for now, because I've already acknowledged your request. So that is the point where the CPU just tells the PIC, okay, I'm here, I'm listening. And the second time, it would actually read the data bus to check for the interrupt vector. So that's the first int A raised. It should go down very soon. We can also just lower down the inter signal. And that's the second time which the CPU actually reads the data bus to check what vector to use for the handler. And that's finished. Now let's see what will CPU do. It takes a while for the CPU to start handling the interrupt, and that's our first ALE after the request. And the address is just, if we just cover these 2 LEDs, because we multiplied by 4, which means that the vector number goes 2 bits to the left. So that is 01010101 multiplied by 4. So that's the offset in the RAM memory to read the address in memory where the handler is located. So that should be a read. Yeah, that's reading from RAM. And as I said, I'm not going to go into the details, but that what CPU is now doing is reading the correct vector for the interrupt 55 hex. That's the fourth and the last byte of the address. And now, as you can see, it addresses the top part of the RAM, which is 7FFF and so on. So that is the stack address. So it does exactly the same as the CPU did in the last video when we raised the NMI request. If you didn't watch it, please, I advise you to do so. So that will be 3 words, which is 6 bytes written to the stack. If you watched the previous video, you would know what bytes they are. And now it addresses F0001D, which is our interrupt handler, first byte of the interrupt handler. That's a NOP, as you can see, 90. And that's another byte written to the stack. As we saw in the last video, some things on the data bus and address bus don't happen as we might expect. That's prefetching of the next instructions. And now the interrupt is finished. And as before, the CPU just reads back the data it stored on the stack before coming back to our infinite loop, finishing the interrupt handler. And there you go, F0017. So it just carries on with our infinite loop after the handler being executed. Again, we saw that things on the CPU buses may sometimes happen out of step and not necessarily tell us exactly what the processor does at each moment. It is also painfully slow to step through the program, and the LEDs don't show us any internal details like registers values. It's time to change this. My plan is to add a text LCD to our computer and use yet another 8086 interrupt to see what exactly happens inside our CPU. The LCD is going to be our first device talking to the CPU using the I/O address space. It means that we will use the high level on the IOM output to tell that the processor wants to talk to it. But it won't be the only device in the future, so we need to be able to address more than this one, similarly to the ROM and RAM chips which we tell apart using the A19 address line. This time though, we will use 3 address lines to tell 8 different address ranges for the future devices. And of course we cannot use the A19 again, because the I/O address space is only 16-bit wide. Instead, I'm going to use lines A6 to A4. If you look at the hex notation of the address, where each digit represents 4 bits, the A6 to A4 bits are part of the second digit, meaning that each of the devices will be addressable by round numbers in hex 00, 10, 20, and so on. You may ask, why don't you simply use the least significant bits A2 to A0 instead? That is because some devices may have more than one addressable register inside, similarly to our ROM having 131,072 memory cells, which need to be addressed using 17 address bits. Therefore, we use the higher bits of the address to choose the device and lower bits to address multiple registers within the same device. Using the A6 to A4 lines to tell between the devices leaves us the least 4 bits, the A3 to A0 for addressing 16 distinct addresses within each of them. To generate 8 chip-enabled signals from these 3 bits of the address lines, we will use the 74HCT138 decoder. It does exactly what we need. It has 3 inputs, and each combination of them sets one and only one of the 8 outputs low. It also has 3 additional inputs to enable the signal at the outputs, which allows us to use them to detect the correct IOM state. We don't want to activate any of the devices when the processor talks to the memory, do we? This is our decoder. The 3 inputs are connected to the 3 address lines A4 to A6. The outputs of the 74138 are active only when the other 3 inputs are in specific states. The G1 on pin 6 needs to be high, and the 2 other pins, 4 and 5, low. I connected these 2 to the A7 line, using them as an additional bit in decoding the I/O addresses. I could as well just short them to the ground. The G1 is driven by the processor's IOM signal, which is high for the I/O addresses. This LCD, like most of the text LCDs available, is compatible with the HD44780 controller chip. This chip allows to communicate with the LCD using 4 or 8 lines of data, together with 3 additional signals. The E, which falling edge, accepts whatever is on the data lines, the RW, which sets the data direction. It needs to be set to 0 when we want to write data to the LCD, and 1 to read from it. The third signal is called RS, and it tells the LCD if the bits on the bus are a command to be executed or data to be sent. The communication with the LCD is performed by sending commands which may be followed by data. Usually, at this moment, other authors would probably connect this 8255 chip, which is the Programmable Peripheral Interface. This IC is an I/O device providing 3 8-bit ports, 24 bits altogether, each of which may be programmed to be an input or output. We may decide on attaching it to our computer in the future, but today I'm gonna attempt to hook our LCD to the CPU directly. It is not straightforward though, as its interface, as I described a moment ago, is quite different. It doesn't have, for example, the chip enable pin, and the E signal works more like a clock. We need to make some trade-offs then. First of all, we will only write to the LCD. Reading is not essential and is commonly omitted to simplify the design. Next, we need to create a contraption which would convert the CPU signals to something acceptable for the E input of the LCD. The E signal, normally low, needs to change to high shortly before it changes back to low for the LCD to accept the data on all the other lines. That is how the WR signal from the CPU works, but its levels are opposite to the E one. We can easily invert it, but also we want the LCD to accept the data only when it's been chosen by our newly built address decoder. In other words, we would like the E to go high only when the chip enable signal from our address decoder is low, and the WR signal goes low when the CPU writes to the I/O port. That is exactly what a NOR gate does. Therefore, we need to use the 74HCT02, which provides 4 such gates. For more details on logic gates, please find my new series on this channel. Okay, so we have our E signal done. The RW will be hooked to the ground, as we will always only write to the LCD. The last to drive is the RS signal. This pin chooses whether we send a command or data on the data lines. So how can we tell the LCD when we send a command or data? We could use one of the available address lines, let's say the A0. This way, from the CPU's point of view, writing a command where the RS needs to be low is nothing but writing to an I/O port addressed by an even number where the A0 is low, and writing data will happen when the CPU writes to the odd-numbered port. Let's build this on our breadboards. Actually, I'm going to use this new breadboard for our LCD. I'm going to put it just on this edge on the right-hand side, like that. But obviously, I need to do the wiring under this before I put it on the breadboard. So we've got this quite standard 16-pin header. The first 2 are power supply. Then we've got the third pin, which I connected this potentiometer to set the contrast of this LCD. Then we've got the 3 control signals, RS, RW and E, and then they are followed by 8 bits of the data bus. The last 2, these are the background LEDs, which we need to connect to the VCC and the ground as well. Let's get to work. Most of the connections are done. These are data lines going to the data bus. I had to maneuver a little bit between those LEDs. This is A0 connected to our RS signal. And the yellow wire, not connected yet, that's the E or enable signal which we need to drive from the NOR gate. The NOR gate, it's here. I'm gonna build in here. I'm gonna use only the first gate, maybe here, because the wire isn't long enough. So that is the output of this NOR gate here. Now its input needs to be driven from both the WR signal of the CPU, which is connected to this red LED, so that's a simple task, and the other one needs to go from the first output of our address decoder, which is on pin 15 here. So this is going to be simple as well. After I connect both of them, and I need to make sure that the NOR gate 7402 is supplied, and then I need to make sure that all of the inputs of the unused gates are connected to either ground or VCC. Initializing this LCD requires sending a few commands to it, so I put together a simple program sending the required commands to port 0, followed by sending some characters to the port number 1, which is supposed to be our LCD data register. Let's see if this works. Let's power it up. That's what you can see on the LCD is the usual behavior before initialization, but we first need to start our program. I will go through it quickly. That's the jump to F0000. We just saw first writing to an AO port, that's to the port number 0. I hope the LCD got that. That's another one. That's 3 writes of initialization. The next will be, yeah, it should be now initialized. The next byte should be written, should be 38. Yeah, that's the command name function set. The next one should be 08 hex, which is display off. 08, that's the command named display off. As you can see, those white bars just disappeared, white 2 rows. So it looks like it's working, because the display just turned off. Another write of number 1, that's clear display. If any RAM memory inside this display was having some random data, it will be cleared. The next write should be number 6 hex. 06, and that is entry mode set. Things like, is a cursor visible, or where should the cursor go? Should it go to the right or to the left? Should it scroll the screen when we put more data? Things like that. The last command we sent should be 0C. And as you can see, that 0C, that turns the display on. And the next write should be to the address of 1, which is the data register of our LCD. And that should be the first character we're gonna send to the display. As you can see, we're writing to the address of 1 IO, so that's our data register, and we're writing an ASCII code for the letter T. There you go. I think it's working. I wrote this program to send 4 letters. After the second, you should be able to guess what the rest would be. Yeah, that's it. I think our display works okay. The next step is to finally build a proper clock generator for our computer and get rid of this little breadboard for good. I'm gonna use this specialized Intel chip 8284. It not only contains a clock generator, but also forms the reset signal using the Schmitt trigger out of the button and the RC delay circuit. I could build both myself, for example like this, but it would take two 7400 chips. The second chip is a counter, because the 8086 needs an asymmetric clock signal with 33% duty cycle. So, to save space on the breadboard, I'm using the 8284, which does all that in one chip. The generator uses a crystal whose frequency must be 3 times bigger than the output clock signal. That's because of the counter dividing the frequency in order to form the 33% duty cycle. Let's build it in. I think we're gonna use this space next to the memories, and I'll put this down. That's our 8284, like that. As I mentioned before, 8284 generates the reset signal from the tactile button, but I have no space around this chip for the button, so I'm just gonna build it next to our 74244, like here. This is gonna be our new reset button. And also I'm gonna use the 6 MHz quartz, which after dividing by 3, because that generator divides the crystal frequency by 3, we're gonna get the clock for the CPU of 2 MHz. I also need to build this RC low pass filter for the button. And finally, the crystal. As I mentioned, I'm going to use this 6 MHz crystal, which will give us 2 MHz CPU clock. The maximum clock for this CPU is actually 8 MHz, but I think 2 is good enough for these tests. Okay, so I think we're ready to test the generator and the 8284 itself. Let me just bring here my multimeter. Let's connect it to the ground and let's power it up. Pin number 12 is the output of the generator. As you can see, it's almost 6 MHz, just as expected, and the CPU clock after the division by 3 should be on pin 8. And there you go, as you can see, 2 MHz. Let's check the duty cycle of that clock. 35%, which is good enough. I think we're ready to supply the CPU with our new clock generator. Before we test our new clock generator with our computer, let me mention for those eagle-eye viewers who noticed some changes on our breadboards. So first of all, I removed the connection between int A and the output enable of our 74244. It is currently disabled for good. I'm going to use this chip in the next video, that's why it stayed on the breadboard. Also, I just hardwired both interrupt inputs int and NMI to the ground, so they are currently not active and won't be active. The second change is the flash. It failed during programming, so I need to replace it with a different one, which is a direct replacement. And finally, I added a few capacitors, decoupling capacitors on our breadboards every here and there. Now, before I can test if the CPU works with the new clock generator, I need to modify my program to introduce some delay loops. That's because we cannot send those commands to the LCD arbitrarily fast, especially during its initialization. Okay, finally, it's time to test our computer with the new clock generator. I'm going to use the old reset button here for now. So I'm pressing this down and power it up. And now look what will happen, hopefully, when I release the button. There you go. What we can see is the program executed correctly, and we've got the test text on the LCD. As a last test, what we can do is to replace the old reset signal with the one coming from 80 to 84, and this should generate auto reset when the power comes on, thanks to this RC delay circuit. But let's try it. As you can see, our LCD and the new clock generator for our 8088 work as expected. In the previous video, I promised you to remove all of the LEDs from our breadboards and change the way we look at our CPU's work. As you might have guessed, we're going to use the new LCD for that. But because this video has got quite long, we will do this next time. Until then, thank you for watching and I hope to see you soon.